we already know velocity field in the system. Maybe if I am trying to look at a two-dimensional world, there is something like x-axis, there is something like y-axis. Flow is coming from one location to another location. And this flow going in the direction of y. Perhaps this entire flow field having a uniform velocity, capital V, but that is going in the y direction. So the unit vector, what we are trying to say is u is equal to v e y. Is that first step clear, Suman?
Yes, sir.
Wonderful. This is the mathematical way usually we show the notation. Now what we are trying to ask is, this is perfectly fine, Raja. Maybe can I really convert just to get mathematical grip from this Cartesian coordinate system into spherical coordinate system? Why we care? Maybe it might be a satellite imagery which gives me some river flow information from one location to another location, which is going in one direction. But I would like to really have a broader perspective on the Earth. So the most appropriate coordinate system might be my spherical coordinate system. So natural choice for me is, though it is going in X, Y, Z kind of direction, especially here in Y direction, can I really look at the same velocity from center of Earth? If I measure it in that radial angular theta kind of coordinate system, how that flow process really transforms. If I put it in this way, the vector like velocity vector, what we are saying is the reality having v multiplied by e bar y. But when I try to look at on different coordinate systems, I might measure the same phenomena with the different values on that coordinate system. It's more like, think of a situation. You are a stationary person trying to observe train speed. Maybe train moving from Kharagpur towards the Calcutta, towards east direction. And you are stationed precisely at Kharagpur. So you know the direction with which this velocity of this train is going. But now think of a situation. You are not at the stationary Kharagpur, but you might be traveling in another train, maybe in the north direction, trying to observe a train which is going from Kharagpur to Calcutta. The same phenomena you are trying to look at, but you perceive it, maybe the train is going in some inclined direction, neither east nor north, but something like inclined direction it is moving. The phenomena is reality, which is moving from Kharagpur to Calcutta, but you perceive it in a other way, like it is having different velocity component. The same thing what we are trying to look at here is, maybe on the Cartesian coordinate system, the real phenomena is happening in that way, but I would like to really visualize it on spherical coordinate system, or vice versa. The reality happening on a spherical coordinate system, but you have perceived it on Cartesian plane. Now, can I really get that one-to-one connection between these velocity components? Is that point first of all clear, Suman?
Yes, sir. Yes, sir.
Wonderful. If that is clear, what we are trying to do is, okay, let me brush up my skill set in terms of Cartesian and spherical polar coordinate system. For that, temporarily, we are switching off velocity field, but we are trying to look at in terms of position vectors, just to see what is the connection between spherical system and our Cartesian system. So first, I am trying to draw something like x coordinate, y coordinate, z coordinate, what I have shown here. In that, there might be a position vector all the way originating from 0 to point P. That radius is R. That means there is a point P connected to O, which we will call position vector. which is oriented in theta direction with the z-axis, and the projection of that P point onto xy plane, if I really get, it is giving me angle phi. Usually these theta phi, we try to talk in terms of something like angular or azimuthal coordinate, and phi as meridional coordinate. These are the systems what we usually talk. Now, is this theta and phi angles, first of all, are you in a position to visualize a p vector which is originator? Once I construct something like xy coordinate, the way if I flip this p towards z, whatever that angle made is azimuthal theta, and if I really literally project that P, OP line onto XY plane, the angle made with x-axis to that projected one is angle phi. Is that first clear?
Yes, sir.
Wonderful. If that is clear, now what I would like to really see is what is the transformation really governs this entire r theta phi in terms of x, y, z coordinates. First of all, let us straight away look at z coordinate, which is easy to begin. There is something like you take pen, fix it on, maybe you use your fingers, the left hand or right hand fingers, make it something like L kind of shape. Now keep this pen at that corner. Try to see that if you can really project that pen towards z axis, what is that we require? That is r cos theta is equal to z. Is that clear?
Yes, sir.
Wonderful. Now, the same pen, what you are trying to fix at your thumb and index finger, now try to project that all the way down to that plane. The plane where your thumb and index on the table are present. Now that angle, what we are calling meridional angle phi. What I have projected is R all the way down. Now I need to project it. That means from vertical towards z direction, if I am projecting, that is cos theta. If I am projecting towards plane, that is r sin theta. Do you understand the meaning of r sin theta first of all onto xy planes?
Yes, sir.
So now that r sin theta component, again we are rotating or projecting it onto x-axis as r sin theta cos phi. Is that clear?
Yes, sir.
Wonderful. Now, the same projected one, I would like to project it onto y also. So r sin theta projected onto y-axis is r sin theta sin phi. Is that step also clear?
Yes, sir.
Wonderful. If that is clear, now let us look at, it's not about, sorry. Okay. It's not about just position vector. It can be even velocity vector, which is u bar. Can you see u bar here? Hello?
Yes, sir.
Wonderful. So u bar also, I can always project it into my x, y, z coordinates. That is the one what I would like to really see for any kind of transformation. That's what we are trying to say. A real physical phenomena like position vector, you are trying to perceive it onto x, y, z coordinates. The real physical phenomena like velocity vector, you want to perceive it onto your radial, whatever this kind of coordinates. From that vector, you would like to really perceive it onto different coordinate system. Now, the real vector, you perceive it on Cartesian coordinate system as v, e, y. Now what I'm asking is how this u real physical vector can I perceive it on radial coordinate system? For that purpose, what I have to do? Take my u vector, project it onto radial coordinate. Is the problem statement first of all clear? So there is a real vector like u, which I would like to perceive it on different coordinate system. Now, because I already have u coordinate system, okay, wait. I already have u. I would like to really perceive it on u or u theta u phi. The same u on xy coordinate system is ux, uy, uw or uvw. It doesn't matter. Now, if I would like to really perceive it on radial coordinate system, what I am supposed to do? Take u vector, project it onto your radial. This is the meaning of dot product. U dot er, I would like to write. U vector is v ey dotting with er. That means the radial vector, what we have tried to really look at point P, if I am going to project it onto y coordinate system, the transformation what I require is my r sine theta sine phi. Is this clear, Suman?
Yes, sir.
Now think of, instead of x, if I am going to put ex, ey, ez. So unit vectors, if I would like to really have it, what I have to really do is sine theta cos. So r is now again a unit vector. That means radius is 1. So that will be projected onto sine theta cos phi, sine theta sin phi, cos theta kind of thing. That is the meaning what we are trying to really look at here. So I'm just generalizing it instead of unit vectors. So ey supposed to dot with er. What is the transformation we require? That transformation is sine theta sine phi. That is this in the radial. Now I am more interested about theta component. What I am supposed to do? Project u component onto e theta. That is for u theta kind of component. That will be my v ey dotting with e theta. That means in the theta direction, I would like to really transform it. Naturally, I will be having that sine theta sine phi kind of component. Similarly, in the phi direction, I would like to really have transformation. I will have that cos theta. Is that step clear? Hello, Suman.
Yes, sir.
I think this is cos theta. So that is the way we transform the coordinates. Okay.
Yes, sir.
Wonderful. Now let us look at second system. Then it becomes so obvious for you to really look at. Now I have a flow field capital U multiplied by ER. This is the flow field what I have. It's a vector. Now if I would like to really visualize radially, you see radially a constant velocity going out. This kind of systems, what we call sources or sinks. Like you have a kitchen tap, you filled it with complete water, suddenly you open that block. All the flow goes towards that hole. So radially, entire flow field really establishes. Such kind of things, either you will call sources or sink. And that flow field, what we are trying to describe by UER. Can you visualize what it means, the flow field in reality? Suman.
Yes, sir.
Wonderful. Now, I would like to really say, okay, I'm not actually working on radial, theta, phi kind of coordinate systems. But I would like to really visualize this entire flow field on XY plane, how it really looks like. On radial plane, everything coming like in the radial direction, I can really see. But can I really represent it on XY coordinates? What we have to do is pick the real vector. The real vector is this UER component. That is this one, the real vector. Project it onto your X coordinate by that dot. So what we are trying to do, UER dotting with UX. If I do that, I will be in a position to really project it onto x-axis and that velocity component, what we are calling U. So ER dot EX, already we have established sine theta cos phi, sine theta cos phi relation. So sine theta cos phi we got. Now V component in the vertical y direction, I would like to really get it. So what we have to do, V component is equal to real vector projected onto that particular y direction. So UER dotting with EY gives me whatever that constant value multiplied by projection of ER onto EY is sine theta sine phi. Similarly, the W component I would like to really get in the Z direction. So U real vector projected onto Z direction. So UER dotting with EZ is cos theta from this relation. Is that first of all clear to everyone?
Yes, sir.
Wonderful. If that is clear, now the tensor of rank 1 or vector, I don't want to write it something like U comma V comma W component, but the typical way like U I plus V J plus W K, I would like to write it in that format. I would like to write it, and that is the one what we are trying to do here, showing the complete Cartesian vector U is equal to UEX plus VEY plus WEZ, which we just figured out. U sine theta cos phi EX plus U sine theta sine phi EY plus U cos theta EZ. This is the way that entire radial coming flow can be visualized on a spherical coordinate system. Many times we may have to jump from one coordinate system to other coordinate system because of simplicity. Why I'm saying that is, think of a situation. If I am giving you this kind of complicated expression, let us assume it in that way. On the x coordinate, y coordinate, z coordinate, the entire flow which is draining from that hole, I'm giving you in this way. Will you be even in a position to really visualize the flow, how it really looks like? It may not be that obvious, but if you immediately think of this entire flow field, radially something like flow is expelling out or radially flow is coming in is much easier for you to visualize. Thinking that Cartesian always be easy compared to cylindrical or polar is just a misnomer. Sometimes visualizing everything comes in radial coordinate system is much easier compared to visualizing something like Cartesian framework. Is that also a point clear? Because of that reason, we are actually jumping around coordinate system. It gives you a bit comfortness unless you practice couple of problems by opening textbook. Try to convert the systems from one coordinate system to other coordinates. It's more like hands-on experience. The essential point is, because in nature, sometimes compared to Cartesian framework, visualizing in other coordinate system might be much easier. That is first point. The second point is, over the time, you might be acclimatized even with computers, trying to do the simulations, do some CFD, large scale simulations. You will be trying to do maybe very complex industrial problems. You are going to really look at it. If you switch from one coordinate system to other coordinate system, you can store lots of data in a very minimalistic way. For example, just to give you, maybe at one point of time, you might be trying to simulate something like flow over aeroplanes or maybe airfoils. I'm just giving an example. You would like to really understand different kind of aerofoils you are trying to really look at. Whole point is to identify how much lift force it is experiencing, how much drag force it is experiencing. You would like to really solve this entire system on a coordinate system like Cartesian, let us assume. This is the boundary where each of these grid points you would like to really get information of U, V, W, P, and so on, so kind of information. For that purpose, you may have to really use something like discretization, try to solve something named partial differential equations on the system. Now, if you are going to discretize, it might, oh, I'm sorry, it's not coming very nice. I'm just giving you a general idea. You try to discretize the entire computational domain into such finite strips, which we call finite volumes. Apply conservation principle like mass, momentum, energy at each and every point of that system. That means complex PD is, you try to write it down for each of these grid points, meshes, and so on. Try to store that at computer like arrays, matrices, and so on, products, minus, multiplications, and so on. So kind of stuff, you try to do that. Finally, convert all these partial differential equation to algebraic equations like AX is equal to B. Try to invert the system to get unknown variables, X unknown variables like velocities, pressures, stresses, and so on, so kind of stuff. Now, if you go it in this way, you lose a lot of accuracy because tackling this kind of curved surfaces by a Cartesian framework, that means if I'm going to zoom it, this entire thing, you are going to span it in that way. That means your grid supposed to be a rectangle. You are going to make arbitrary kind of triangles, very curved kind of thing. So when you are going to use something named Taylor's approximations to really discretize the thing, you lose a lot of accuracy. So in that case, and it takes very good amount of storage to even solve such kind of problems on computers. For that purpose, what people try to do is check out this entire Cartesian coordinate system, maybe try to construct a new body fitted coordinate systems. We are slightly taking a digression, but that's also important sometimes. So you try to construct something like body fitted coordinate system. This is non-orthogonal, neither x, y, z, nor r theta phi, nor r theta z. It is a new kind of coordinate system where matrices, not matrices, but matrix comes into picture. You carefully construct all these approximations in a very nice way. Something like that kind of systems, you try to really construct it so that each and every point of the domain you will be in a position to really construct it. This takes very less storage, highly efficient way compared to your Cartesian. In that case also, you may have to jump around the coordinate system. So one, by any means, because it's just a beginner's course, it's just a beginner's course. So what we are trying to do is, can I first of all get comfortness in terms of Cartesian framework? Is that fine? jumping around Cartesian to spherical, spherical to cylindrical, and so on. Guys, am I audible? Am I clear? Not clear?
Yes, sir, you are clear.
Wonderful. So that's one of the point why we jump around these coordinate systems. Fine. Now, let us look at one more example. After that, we will begin our deformation rate and so on, so kind of stuff. Now, let us look at another example. Because these are mathematical techniques, what we want to really get acclimatization. No science, not that much science involved in that. But sometimes these learning mathematical techniques is also important. Okay, let us begin with second problem. There is something like a fluid particle. It is moving in a steady flow, and especially it moves along x-axis. And its distance from the origin is r0. That's at time t0. And its trajectory is r of t is equal to k multiplied by t minus t0 plus r0 cube whole power 1/3. How do we get? After measuring, after doing experiment, after measuring it only, we will get to know. Here, k is some proportionality constant, having something like volume per time, something like that. If that is the case, can I really find Eulerian velocity and acceleration? And also, can I show that this Eulerian acceleration can also be obtained from d by dt of u of x? First of all, is the problem statement clear? Something like there is a fluid particle. It can be 1, it can be 100, it can be billion, but somehow you are doing an experiment. You figure it out. You identify something like a colored particle that moves only in the x direction. But while it is moving in the x direction, its velocity might be changing. It may not be a constant velocity. At this location, it might be some velocity. Next instant of time, it might be having different velocity and so on. And it has originated at r0 location. And as a function of time, if I'm going to measure this entire particle displacement position, I can really describe by this functional relation r of t. This is only for the fluid particle. That's especially for one fluid particle. In case, if I just know that one fluid particle which is originated at that location, throughout that xy plane or x plane, how the flow really happens on the system. Think of a situation, river is moving from one location to another location. You just left a leaf on one location. You all the time tracking that leaf position. The leaf sometimes goes very fast, sometimes goes very slow. And all this position, what we are trying to look at is only in the x direction, because our camera can only capture one of the coordinate system, but I cannot really track the other coordinate system. The way how I can arrange this coordinate system, maybe I might be on that shore. River is moving. I just fixed the camera at one location. So I can really visualize some 10 meters of span. But I cannot really see the width of the river. That is the way I might have arranged the camera. So leaf comes from one location, goes in other location, though it might be doing some two-dimensional motions and so on, because the way how I have set up the camera is, it can visualize only x coordinate, but it cannot visualize y coordinates. And that position of the leaf, when I am going to track, it follows some functional form. If that is the case, knowing that leaf information, can I really say what is that fluid information from that location to other location? That is the question what I am trying to ask myself. Is the problem statement first of all clear to everyone?
Yes, sir.
Can you distinguish what is Lagrangian frame, what is Eulerian frame now?
Yes, sir.
What is Lagrangian frame in this case for this example? Hmm?
So the particle.
The leaf, precisely. The particle or the leaf is the Lagrangian coordinate, I know. Information, the position of x as a function of time. What is the Eulerian field here?
So the fluid information.
Precisely. So the leaf which is resting on that fluid information. By just knowing leaf information, I will be in a position to really say about that fluid information. That is the power what Euler has connected from Lagrangian to Eulerian. Now, if that is the case, first of all, try to visualize this entire mathematical relation in terms of a picture. The x coordinates and maybe time coordinate, I would like to really put it in this way. All the time I can measure only x coordinates as a function of time. So the particle at that given instant of time, this is at that given instant of time at that location. Over the time, if I'm visualizing that leaf is moving in time, that perhaps went it in that way, going in that way. It can again come back also. We don't know. But time always increases. So this possibility is not there. It can really come back to its original position if it really takes in the other coordinate direction. Fine. If that is the case, now let us look at what is this particle velocity. dr by dt, if r is the trajectory of that leaf, dr by dt gives me the velocity information of that leaf, the Lagrangian velocity. So dr by dt, I will be in a position to really calculate k by 3 multiplied by k into t minus t naught plus r naught whole cube whole power minus 2 by 3. Is this information clear? The Lagrangian velocity of that leaf?
Yes.
Wonderful. This supposed to be equal to the local fluid velocity at that particular given instant of time. And the local fluid means the fluid which is just below that leaf. That is the local fluid. And that velocity supposed to match with my leaf velocity, because leaf is carried by the flow. That means if I measure the leaf velocity, that means I'm actually going to have that local fluid information. So that supposed to be equal to my Eulerian field information u of x. Leaf is moving. Just below the leaf, it is at a given x location. That location, what is Eulerian velocity field? That's supposed to match. That is the way we calculate. We will come back. Now, once I know the Lagrangian velocity, that is this, I can always calculate Lagrangian acceleration also for that leaf as d by dt of leaf velocity, which you differentiate it, you will get minus 2k square by 9 multiplied by k into t minus t naught plus r naught cube whole power minus 5/3. Now, we would like to really find out Eulerian velocity field. Now, as we already know, the position of the leaf is r of t. And just below that, I'm going to really track what is that x location of that leaf. X are the Eulerian field information at that location. That's the reason I use different symbol, capital X bar. This position vector can be even X, it can be Y, it can be Z. But just to give you idea, the position vector of leaf in terms of R, and it's a one-dimensional coordinate system. The Eulerian velocity information is still it is R, but at that given X location. That's the reason we have used separate symbol. As long as we know what we are trying to do, this notation doesn't matter. Now, just below the leaf, what is the velocity? That velocity is supposed to be the leaf velocity or vice versa. So that means what we are trying to do, my Lagrangian leaf velocity when X, where I am going to measure, is just at the leaf location, same as my Eulerian velocity field information. If that is the case, what I am trying to do, begin the step. What is my u of t when x is equal to r of t? That is this relation. Already we know what is our u of t. K by 3 multiplied by k multiplied by t minus t naught plus r naught whole cube whole power minus 2 by 3. This, when x is equal to r, we would like to really calculate it. That means what we are trying to do is, here position vector, what we have is, look at this, when r naught k multiplied by t minus t naught plus r naught cube is my r, this entire thing is my r power 1 by 2. So this is r power minus square. This entire relation we already given as power 1/3, including this, is my r. So that r, what I am trying to write, k by 3r square. Is this step clear? First of all, to everyone. Hello, guys.
Yes, sir.
Wonderful. So my Eulerian velocity field is k by 3r square when x is equal to r, which is k by 3x square. So what we are actually achieving it is, I really don't care about the leaf where exactly it originated. What is its precise location? I don't worry about that. When I am going to measure it on Eulerian system, what I will measure on Eulerian system is, you just tell me the location X. You just tell me the location R. I will be in a position to really deduce that expression. And that expression, what we got as k by 3r square or k by 3x square, independent of where exactly it originated. That kind of transformation what we have done. That means you specify x is equal to 0, x is equal to 1, x is equal to 2, x is equal to 3, and so on. The velocity gradually falling. That means at far away x, it is far away means very origin, it is having quite high velocities, but as it is coming, its velocity gradually decreasing in that direction. Maybe it might be trying to climb up a hill, maybe climb up a land, maybe it's something like it's going to sense a wall next to it. Very high velocities, gradually it is going to slow down, reaching the wall. That is the information what we got with velocity. Velocity field, Eulerian field. Now let us look at acceleration of that leaf and acceleration of the flow field. So that is acceleration of the particle is this, and acceleration of the flow field is a of x. So already we have calculated what is this information in terms of acceleration of the system. So r power minus 1/3, that means r power minus 5, that is r power minus 5. So we are trying to convert all these origin coordinate system into our Eulerian kind of system. So it is minus 2k square by 9 r power 5. In terms of x coordinate system, it is minus 2k square by 9x power 5. Okay, now what we are trying to do is, that's why all the time we have to really look at this Lagrangian kind of system. Can I really look at directly on the Eulerian field if I know Eulerian field information? Someone was talking. Yeah, Druhin. Okay, maybe mic disconnected. Fine. So now directly, if I would like to calculate this Eulerian velocity field, Eulerian acceleration field, we already know the complete acceleration of the Eulerian field is del u by del t plus u dot del u, which is equal to our Lagrangian acceleration. So what I will do, let me straight away calculate what is del u by del x here and calculate u dot del u. So del u by del t is, because it's independent of time, value is 0, u del u, so it is one dimension, so u multiplied by del u by del x. So u multiplied by del u by del x is this, k by 3x square u multiplied by del u by del x. So del by del x of k by 3x square, which gives me minus 2k square by 9x power 5, which is nothing but, if I straight away calculate du by dt from a of t, both the things match. Great. So let us look at something named another example. Find equation of streamline in 3D. Because we have something like 1 hour for tutorial, 1 hour for class lecture. So we are more or less going interchangeably. Now, can I find the equation of streamline in 3D? We will derive something like the equation of streamline in 3D is dx by u is equal to dy by v is equal to dz by w. Think of in 2D. That means you may have to mask the 3D information. If you mask 3D information into 2D, dy by dx is equal to v by u, which is equation of streamline in 2D, right? And that is the thing what we are going to show in 3D systematically, why it should have such kind of form. Streamline is on Eulerian field. Path line or Lagrangian particle, this kind of information is for Lagrangian coordinates. So the basic definition of streamline is, there might be some imaginary curve, the purple one, where pick any local point, measure velocity. At that location, the velocity vector is v bar. And it might be having some position vector. The point where I'm going to really measure is, there always be some position vector. Let us think of it in this way. XYZ coordinate, laboratory fixed. At some location, I'm going to really measure that point is at R position. A tiny infinitesimal location where that flow line or perhaps a streamline moving, that position vector is R plus dr. Because there is something like a line, mathematically, if I would like to really represent, I need to have something like dr kind of infinitesimal strip. Then only I will be in a position to really call it like a line. Though arbitrarily I'm drawing a big line, at math level, calculus level, if I want to really describe something like a line, I require some infinitesimal coordinate system, that is my dr. And that dr I'm going to pile it up one after other so that I can really span a line. And that dr also tells me a tangent geometrical tangent to that line. Is that point first of all clear? The position vector r, an infinitesimal position vector r plus dr. So that vector which connects r and r plus dr is dr. That's supposed to be the position through which streamline is supposed to pass. So that dr is a tangent line to that position at that location. So the geometric description is dr. The kinematic description is, if I really measure local fluid velocity, the tangent supposed to be given by my velocity. So using these two information, we are going to construct something named streamline. Now think of a situation. The tangent dr, the velocity vector v bar, in some sense parallel to each other. In that case, Raja, why can't I really multiply my dr by proportionality constant k to say spanned by velocity vector v bar? That is the natural question we can really have it. You understand what I'm trying to say? Geometrically, you know the tangent dr, that is the direction with which it's supposed to have a slope, and in the same direction v bar is there. But I cannot really replace v bar is equal to some proportionality constant multiplied by dr, because the dimensions matter a lot. One is meters, other one is meter per second. So I cannot really connect these two things geometrically in a direct way without using calculus. If I have the dr by dt, then I might be in a position to really connect v bar. But dr by dt has meaning saying that there is something like a Lagrangian particle which is moving. So I cannot really employ that calculus. So the clever way, what people have figured out, you have geometrical quantity dr, you have kinematic quantity v bar, they are parallel with each other. So naturally, these vectors supposed to be parallel means dr cross v bar supposed to be 0 bar. This is supposed to hold. Is that point clear? Hello? Otherwise, it's just more like math class where you remember the formulas rather than appreciating how people actually went ahead to construct such kind of mathematical relation. If it is not clear, this is the right time to really spend.
Sir, can
Sindhuja.
you please repeat it again?
Okay, fine. Let us think of, I'm giving you a rope. Don't worry about whether it is fluid mechanics or not. I'm giving you a rope, or maybe you have earphones line, the wire. Think of that earphones line is that violet or purple color line. I want to really specify that earphones wire in three-dimensional system at any given point. That point on the earphones line is r bar position vector. At math level, if I want to really talk about this earphones line, the one thing is I need to specify function. What is x, what is y, what is z, how these x, y, z are connected, so that whether it is x, y square plus z is equal to constant, or x, y square is equal to constant, or x is equal to y square, some mathematical function I need to give to really talk about that earphones line. But that becomes very specific example. An arbitrary example is there is a wire, any point on that wire given by the position vector r bar. That is this. Wire has continuum. That means the next point also have wire element. The next point also wire element. That means the wire element, infinitesimal thing, if I would like to describe, the easiest way what I can really describe is it has dr bar vector. That tells me the precise location of that tiny wire element in that arbitrary plane. Is that clear?
Yes, sir.
Wonderful. If that is clear to us, now what is the direction of dr? I need to really check. The direction of dr is, because I already have a wire, if I have any particular dr, that is the direction in which wire is propagating or wire is present. That means that is the direction with which my slope gradually increases or decreases on the wire. Is that also clear? I
Yes,
don't
sir.
know precisely what is the slope, but I know that the dr direction supposed to be the slope direction. Clear?
Yes, sir.
Wonderful. Now, let us come out from the geometry, move on to kinematics. Now, instead of your earphones wire, think of there is some arbitrary fluid streamline. What is that streamline? We will see. Now, let us come out from that wire, the geometrical argument, try to come on to kinematic arguments. There is some arbitrary line, streamline, which we are going to really describe. We don't know how it really looks like. But point is some arbitrary line. The definition of a streamline is you pick any point. The tangent, if I am going to draw to that, supposed to give me information on the velocity field. If that is the case, my velocity field information tangent is v bar. At the same time, the geometrical argument is dr bar. So both supposed to be parallel to each other. This tangent, that tangent supposed to be parallel to each other. They may be one and the same, they may not be one and the same. Why I'm saying they might be one and the same, they may not be one and the same. On one side, a geometrical level, we are talking in terms of lengths, meters. Here, for streamline, what we are talking is meter per second. So I cannot really say that dr bar multiplied by some constant value like scalar a is my v bar, because dimensionally it is wrong. So the next option what we end up is dr bar supposed to be parallel to v bar. That means two vectors parallel to each other. Possibility is dr bar cross v bar is equal to 0. This is the only possibility. There is other possibility, but that's not really possibility is because I know dr bar. Why can't I differentiate it to my same dimensional numbers like meter per second by saying dr bar by dt? But now the question comes, a geometry level when you are talking dr bar, that talks about that infinitesimal object. But dr bar by dt meaning is that object is moving with a velocity v bar. Whether that happens or not, we don't know. That's the reason we are not saying taking d by dt of r bar. That is meaningless unless the material really moves. So the only possibility what we have is dr bar and v bar parallel to each other, and dimensionally they are not equal. So the chance at math level to write is dr bar cross v bar is equal to 0, but not dr bar is equal to a multiplied by v bar. Is that argument clear?
Yes, sir.
Wonderful. If that is clear, now let us think of your whatever algebra, I mean tensor algebra you have learned. Maybe if you are comfortable in terms of initial notation, dr bar cross v bar is epsilon ijk drj vk. The values, if you are going to write it, w dy minus v dz, u dz minus w dx, v dx minus u dy. Still you are comfortable with the cross product like e1, e2, e3. dr is dx, dy, dz, crossing u, v and w. One and the same, what we are going to end up with. Yeah. So if you simplify dr cross v bar is equal to 0, this entire thing supposed to be 0, this entire thing supposed to be 0, and this entire thing supposed to be 0. That means dy by v is equal to, from the first relation, dz by w. dz by w is equal to dx by u. dx by u is equal to dy by v. That means dx by u is equal to dy by v is equal to dz by w, supposed to be the equation of streamline. Is that clear? Guys, Sindhuja.
Yes, sir.
Okay, wonderful. Now let us just begin a small problem in 3 dimensions, 2 dimensions, to really work out that streamline. Can I find it? So maybe u is equal to x by t plus t naught. With the time, at a given x location, the velocity gradually decreases. It's an unsteady flow. It depends on time. And this velocity is nothing to deal with particles. In most of our fluid mechanics, we don't handle Lagrangian. We all the time talk only in terms of Eulerian. But because these are initial lectures, to connect Lagrangian to Eulerian, we discuss still Lagrangian and Eulerian. But most of the time we discuss only Eulerian because it's easy to visualize, easy to understand, easy to find out. So you take a probe, you keep it at a given x location, try to measure what is the velocity. What you are going to see, as time increases, velocity decreases. At other position, as you increase position, maybe velocity might be high. This velocity in the x direction is u component, and that velocity in the y direction is v naught constant, and w is equal to 0. So equation of streamline is, and especially we would like to really find it at t naught time, t is equal to 0. So equation of streamline is dr cross v is equal to 0, which is dx by u is equal to dy by v is equal to dz by w. dx by u is dx by x by t plus t naught, dy by v naught, and dw by 0. This is the equation of streamline. Now separate out these two. dx by x is equal to dy by v naught multiplied by t plus t naught goes. Now integrate it separately. Log x is equal to y multiplied by 1 by v naught multiplied by t plus t naught. So you replace that proportionality constant e power and so on so thing with coordinates. Then x is equal to some proportionality constant multiplied by e power y by v naught multiplied by t plus t naught. When t is equal to t naught, the equation of this streamline, what we get, x is equal to a e power y by v naught t naught. So think of it in this way. There is some reverse stream is happening. Locally, when you are measuring, this river is not a continuous thing. Maybe you just discharged water. At that time, you see a lot of velocity. But as time is approaching, you are going to close the valve. So local velocity is going to decrease. But that flow, think of something like there is a pipeline, there is a valve. Let me draw it. This is the pipe. There is a valve. At time t is equal to 0, there might not be anything. You suddenly opened it. Water start gushing. Now you measure here. There is no velocity. But over the time, and suddenly you close the valve. So a patch of fluid really gush, goes over the space. You start measuring this at the time. This gush really cross the system. Gradually, it start decreasing at this location. It approaches 0. That is the relation what you are seeing here. Can you sense that? As time increases, this velocity gradually decreases and reaches to zero. It's more like you suddenly opened a valve, some gush really happened, and you suddenly closed it. This gush may be moving with same velocity, maybe varying velocities might be happening. Lots of breakdown and so on, so kind of thing. The gush is moving. Now, if you look at any given instant of time, the velocity of this flow here, the velocity of the flow here are different. That is the one what it is giving. Larger distances, larger velocity. Shorter distances, shorter velocity. Is more like a valve which you suddenly open and discharged. That can be mathematically described by this form. Now the question comes, how do I know only this particular kind of format? For that, you require something named conservation of mass, conservation of momentum, and so on. When you solve that, perhaps you might have got this relation. But to reach that stage, first of all, we should be a bit acclimatized with mathematical notation. And what we are doing is reverse process. Already I know that if that is the case, what will be that? Now you think of it in the y direction, that is in this direction of that one. Maybe most of the patch have same velocity in that y direction. That is this v naught. A gush really comes throughout that gush, same velocity in the y direction, but it has a velocity different in the x direction. If that is the case, can I really describe its streamline? And we have deduced the streamline information. And now, if you use any mathematical program, computational program, one can really plot this x versus y information at a given instant of time t is equal to 0. Because it's exponentially increasing. That is the way you will be in a position to really see this streamline. Think of other example. There is a crosswind and there is a streamwise wind. Both the things are acting together. That means this entire flow really shifted in the plane in that particular kind of format. So this wants to go in this direction and also there is subjected to crosswind. So naturally flow start moving in that direction. That is the thing also what we try to visualize. Again, we will come back to little bit part of kinematics, what we call fluids under deformation. Initially, we described something like the Newton's equations have to be modified because there always be objects like infinitesimal elements. Unless I know stresses, unless I know strains, I will not be in a position to really write down conservation principles. To do those conservation principles, we require little bit tool sets like this kinematics, try to understand what it means velocity field, what it means stress field, what it means deformation, how to write these constitutive equations and so on we are heading for. Now let us consider an example where a sea wave is breaking. And that's the thing what I have shown here. Within that, I'm going to zoom into fluid part. There is a tiny infinitesimal element. That if I'm going to zoom, it looks like very big object. The faces like violet phase, orange phase, blue phase, and backside phases, and so on. If there is fluid element in the sea, moving from one location to another location, experiencing acceleration, experiencing something like deformation, like how sea wave is breaking and so on, so kind of thing, naturally, it must be subjected to forces, but these forces manifest on this infinitesimal element phases as stresses. And we have seen that the stress tensor is a second rank tensor. Now, if I would like to mathematically represent that, the standard convention is you pick any phase, maybe the blue phase, that is this phase. Try to identify what is the surface area direction. In this case, it is in this blue line, which is x. What is the force acting on that? Whether it is acting or not, that we will see. But in case if there is a force acting on that system in a complicated way, maybe one of the component is x direction it is acting. Then the stress component, because of this force which is acting normal to that surface and the plane is in this direction, the stress force per unit area for that particular direction, I will show it as sigma is the stress component. The direction of the area, blue directional area, x, and the force direction also x. We represent or move with that kind of convention. In case in this kind of complicated sea wave breaking phenomena and so on, so kind of stuff, if I take infinitesimal element, in case randomly many forces are acting on that, that infinitesimal element is getting stretched, experiencing forces, accelerations, and so on, so kind of stuff. That entire force really distribute on that infinitesimal on these areas, especially one of the area what I am trying to take is blue area. Maybe one of the component of force act on that particular surface in the x direction, and the surface area normal direction is also x direction. So the force component which is acting in the x direction normal to that plane, what we are representing as sigma xx. The first component always be area direction and the second component is always be the force direction. Similarly, if other force component acts parallel to this surface, the force per unit area I'm talking as sigma, area direction is x, force direction is y, so sigma xy. This is the way I will represent. Though force, we talk about center of mass, that might be distributed because that never exists, and that has been distributed on many surfaces in arbitrary directions. Like think of our cantilever plate, where force is trying to stretch, where force is trying to shear, force is trying to rotate it, and so on. Such kind of forces on that surface, if they are acting, first we are trying to mathematically write down, track them. The standard convention what we are following is first index always be area direction, second index is the force direction. Similarly, the force which is acting in the z direction but on the surface direction of x is sigma xz. Is the convention first of all clear? Anil Vaishnav, Chetan, Vamshiraj, Ayush Lohani, Aryan.
Yes.
Wonderful. Now, if that is clear, let us look at orange surface. On orange surfaces also, forces are distributed. Maybe some of them normal, some of them tangential, or on that plane, they might be acting. So let us do that step by step. The surface direction, can you tell me the orange surface direction? Hello? Guys, can you tell me what is the direction of orange surface? It is y direction. Because of that, any stress component, if I am talking about sigma y as the first coordinate index, the second coordinate represents force direction. So the force which is acting in the x direction is sigma yx. Similarly, the force which is acting on y direction on that particular surface, sigma yy. Similarly, the force which is acting on that surface in the z direction is sigma yz. Is this clear?
Yes.
Hello?
Yes, sir.
And the way you calculate is, you know the force, you know the surface area in magnitude. You divide it, you will get sigma yz. The representation is standard convention, normal, and in one particular plane directions. The arrows can be flipped in the other directions also, but generally we begin it in that way. And this, one can even think of a rocket is trying to move, exhaust gases are coming down, fluid is getting deformed, creating reaction forces, so rocket is moving up. If I am going to take the tiny element, how much momentum flux it carries, what kind of stresses act, for the same thing, I will be in a position to represent. It doesn't matter whether it is naval kind of problem, or is it something like aerospace kind of thing, or maybe something like a fluid spray happened into this agricultural fields. Doesn't matter. But that mathematical information we are trying to talk. And what you have to remember throughout the course is the first index for stress is area direction, and the second index is for the applied force direction. And if this material is always in equilibrium, neither accelerating nor getting deformed, the three phases front what you are seeing, the same thing repeats in the opposite directions on the backward faces. In that case, the material will be under equilibrium. If the frontal faces information what we have written exceeding the backward faces, the material may start getting stretched, deformed, rotated, and accelerated. That is the way the tiny points what Newton said that something is getting accelerated happens. So the fine scale description of Newton's mechanics is trying to look at these infinitesimal elements, write down the stress distribution on these surfaces as components. And these 9 components, if you are going to compare, on each of this phase, you will have 3 components. The total 9 components actually represented at a given point. So this infinitesimal, if I further zoom out, it looks like a point. Newton level is that point, experiences forces because the stress is at infinitesimal distributed on that element. When you add all these surface forces properly multiplied with areas, then you will be in a position to represent equivalent force F is equal to sigma second rank tensor condensed onto particular area. Whatever that surface, you will have it. If you add all these surface areas with sigma dotting with A, you will get effective force on that element. Fine. That is the point what I'm saying. Whenever external medium apply coerce effective forces, the fluids under consideration subject to deformation. Now the natural question really comes, in case somehow I know these external forces acting on that, how much surface experience stress? How much elongation happens? What might be the strain rate? What is the relation between the stress and strain? That has inspired these fluid kinematics guys to go further into details. And what they have figured out, when such kind of force combinations act on that, fluid elements might really get elongated, they might be compressed, they might be rotated, they might be sheared also. It's not only specific for fluid mechanics, even for solid mechanics, any continuum media, whenever you somehow create these forces on the materials, materials start responding by showing this kind of combinations. Unless we know that deformation, we will not be in a position to really know the transport phenomena of that process. Unless I know how fluids really discharged, what kind of crazy motions happens, I will not be in a position to really sense what is the reaction force this rocket really experience. At +2 level, it's quite easy to say that the fluid velocity which is coming out is so and so kind of thing. If that is the case, calculate the reaction force. Is pretty straightforward problem. However, based on how much mass it is going to discharge, the local fluid velocity might change. They might start showing instabilities, turbulence, lot of crazy structures they start showing. Whenever these additional structures and so on, so kind of things are happening, it's not obvious to find such kind of +2 fluid mechanics velocities. The whole point comes there. We in principle don't know how those structures which are coming out of that rocket engine, and that information supposed to come out from evolution mechanics, writing conservation principles. Unless we write that, unless we understand the structural information of fluid mechanics, how they interact with each other, what kind of stresses and so on, I will not be in a position to integrate this entire volume to really describe the overall force coming out of the system, so that I can really calculate my reaction force on the system. This is the problem what fluid mechanics guys does, and why it was so difficult science also because of that phenomena. It might be so easy, nice to appreciate rockets, missiles, bullets, projectiles, and so on, so kind of stuff. It is very fancy to work out those details at +2 level. But you may not be in a position to design the objects unless you understand the flow phenomena, what is happening around this object, how this discharge is happening. You will not be even in a position to design better things. To really know the structural information, you cannot really copy it from somewhere. It depends on many factors. The combustion instabilities, whatever happens inside the rocket, the intricate design of that rocket engine, the flexibility of that rocket, the kind of fuels what you use, how much mass you are going to burn it, what is the surrounding atmosphere condition, many things really affect. Even whether earth has rotation, whether earth rotation is going to change, these things also affect it. So unless we really understand all these structural information around this rocket in terms of fluid, we will not be in a position to really set that rocket to move in the same way. If that is the case, how I will be in a position to really disentangle each and every building block of that structural motion. And those building blocks, what we are trying to look at, elongation, compression, rotation, shear, and so on. So now think of a parallel example. If I am giving you something like a material, maybe ceramic thing, maybe TV, maybe computer, whatever that, the building blocks are atoms, maybe molecules, or if you are going all the way down, subatomic particles, maybe all the way down, maybe strings. Those are the structural identities. Unless you know, you may not be in a position to really understand what is that constitutive material happens. Now, whether that is required to understand, to design something or not, that's different story. But people try to really go all the way to those small details. This is the way the structural information really looks like. And that structural information, what we are trying to look at as deformation. Especially, this has inspired even at Newton level to propose something like Newton's law of viscosity. We don't know precisely whether Newton is aware of the stress distributions or not. Later on, people really realize the stress distribution, deformation rates, and so on, so things exist. And for that purpose, what people used to do is They take fluid in between two plates, parallel plates. One plate is fixed, other plate you try to slide it. In between that there is a liquid. Now try to measure how the velocity changes across the gap. That is the thing what we are seeing here. And first thing what they have observed is any fluid layer supposed to be in contact with that plate. If plate is moving, fluid also supposed to move. If plate is rest, fluid also at rest. That condition, what they made was no slip condition. This is the observation. Whether it happens or not, that's a different story. But what people have observed for many of the configuration, liquid layers, fluid layers, air layers, whatever that, always be in contact with the materials and they will go with that plate or material velocities. If plate moves, fluid also moves with the same velocity. There will not be any discontinuity in the velocity. And what they have figured out, when plate is moving at slow speeds, linearly velocity increases in the plate. So this is the one, what I mean. At plate velocity is equal to 0. As you go up, the horizontal velocity component increases. Which velocity component? Horizontal velocity component. In which direction it increases? It increases in the vertical direction. So think of velocity is horizontal, but that have a dependence on y direction. You may not have vertical velocity. Vertical velocity is 0. Vertical velocity is 0. Vertical velocity is 0. Vertical velocity is 0. And everything is Eulerian field. That is the first observation what people have figured out. And second thing also they try to do, pick concentric cylinders. Two cylinders, fill it with liquid, close it at bottom, rotate outside cylinder or inside cylinder. Try to sense across the gap what is the velocity changes. If outside is moving, inside is stationary. If I am looking from top view, the outside cylinder moves, so velocity is in that direction. Inside it gradually decreases and velocity becomes 0 at center of that place. And this is u theta component, azimuthal component, and this is the radial direction. This is the component. Again, they have observed linear velocity profile for small rotations. You apply the torque outside, measure inside the liquid velocity, still they show linear. And they finally concluded two observations like fluid layers in contact with the walls always stick with each other, and that's what they call no slip condition. And the other one is layer by layer deformation takes place. That means you zoom up this portion. That's the thing what we are showing here. The fluid layer which is in contact always be at rest. The top layer moves, the top layer further moves, the top layer moves further, the top layer moves further. And the top layers experience higher velocities compared to the layers which are in contact with the fixed plate or fixed cylinder. This is the second observation what they have observed. Based on these two observations, what they try to argue is, can I really measure the shear stress? And this is the component what they call shear stress. Moving plate, you are trying to shear the liquid in between these two plates. So force is in this arrow direction. The plate direction is normal to that. Plate direction is normal to that. So that's what we are trying to show here. Force is in this horizontal direction, X direction, and plate is in the Y direction. So the force or stress component, force per area, if I am going to represent, first index is Y, because plate direction is in the Y direction and force direction is in X direction, sigma Yx, which is equal to force per area of that plate. They try to plot as a function of deformation rate. Deformation rate means measure your local velocity as a function of y. Now calculate del u by del y. That means u components you are going to measure. Calculate del u by del y. Particular gradient in the y direction. The gradient is high here. Gradient gradually changes. If it is linear, del u by del y is equal to constant, and plot that del u by del y. Can you see the plot? What we are trying to do? Plot how much applied shear stress versus deformation rate, which is del u by del y, in a very loose way. Or you measure del u by del y, calculate what might be the shear stress required. Either way, what people have figured out, shear stress proportional to shear strain rate or deformation rate. If that happens, such kind of systems, shear stress proportional to shear strain rate, called as Newtonian fluids. If they are not showing shear stress proportional to shear strain rate, they started calling non-Newtonian fluids. For example, if I am going to take water in between plates, try to shear, based on how much shear stress, proportional shear strain rate I'm going to get. The velocity gradient also happens in the same way. Then we will call Newtonian thing. You put honey in between these two plates, try to shear stress. Maybe you might require larger shear stress to create the similar kind of shear rate or shear strain rate. And that changes based on how much stress you apply. So it is in some sense non-linear. Let us look at that. Not proportional. This is also not proportional. If that is the case, we call non-Newtonian fluids, and the technical names, they will be called as pseudoplastics or diluents. Your blood, which is passing through arteries, veins, and so on, follows one of the special case like this non-Newtonian thing. The teardrops may be Newtonian. Maybe the river waters, Newtonian fluids, where applied stress proportional to strain rate. It has very big consequence in terms of transporting materials from one location to another location, transporting heat from one location to another location, transporting dissolved carbon dioxide from one location to another locations. Okay, your heart, what kind of stresses it has to really create to pump blood through arteries, veins? What kind of stresses, muscle contractions, and so on, so thing supposed to be created by your lungs so that air really goes, try to dissolve into blood. Air means oxygen. How it really exchange carbon dioxide. Maybe how your rocket engine transport these properties. All these things depends on what kind of stresses, strains it creates. And in 17th century, empirically, people try to call shear stress proportional to shear strain rate. Del u by del y, units are meter per second by meter, which is 1/second. If that happens, can I replace the proportionality constants as shear stress by shear strain rate as a constant named dynamic viscosity. This is the way they have defined something like viscosity of a system. Now these things what we are learning is something like 16th century, 17th century kind of science, where atoms, molecules were not exist or not discovered. People were not aware of these atoms and so on, so kind of thing. Collisions and so on, so kind of things also, people are not aware of it. You might think of pressure, viscosity, all these things in terms of how strongly these molecules bind and so on, so kind of stuff. But at that point of time, like 16th, 17th century, they were not aware of those things. So they try to really measure them. My kinematic viscosity is this much. My pressure is this much. My thermal diffusivity is this much. By doing these engineering problems, they try to figure it out transport properties. Nowadays, it is very obvious to really talk about viscosity means maybe molecule try to rub it and try to create it and so on, so kind of thing. So there must be viscosity. It becomes so easy for us to understand at this point of time. When this kinetic theory of gases, molecular motions have been established in 20th century. Before that, people had very difficulty in terms of appreciating what it means viscosity, why fluids really behave it in that way. There is no reason for it other than observations. But still, based on those observations, people try to quantify mathematically. You understand the issue? Hello?
Yes.
Think of a similar example. Saying something like molecules, atoms is very obvious for you these days. But if someone says something about extra dimensions, can you really imagine what it means extra dimension? What it means string, which really makes something like atoms or subatomic particles like protons and so on, so kind of stuff. Can you imagine that? It's not that obvious, at least till 1960s. Whether that really exists or not, also we don't know. That kind of dilemma, what this 16th, 17th century really faced. What it means viscosity. I'm measuring, I'm getting it. I say something like some viscous action is happening. What it means, I don't understand. That kind of dilemma helped them to construct furthermore and furthermore mass to really describe the process. Okay?